Our project is improving latent representations via explicit disentanglement. Next slide. Motivation. So we learn in class that generative models are able to capture high dimensional representations, but these are often black box and uninterpretable, so they're hard to generalize for downstream tasks. This motivates the need for explicit disentangled latent representations.
So we can begin by setting up a factorized setting for VAEs, where instead of just having one latent distribution decide what a data point X is, we have two factors. We have both a latent distribution and a factor distribution containing explicit information that we seek to disentangle from the latents Y.
So our first method for doing this is an explicit similarity loss. And so we have X prime, where X prime is same as X with the factor change, usually with an augmentation. And we have outputs from the encoder, which will be Y, Z, Y prime, Z prime from this previous slide. And the idea is to add a KL loss that minimizes Z and Z prime, because these latents should be the same while the factors, Y and Y prime, should differ.
Another method that we use is forward cycle loss. The same idea as before, where we have X and X prime, which vary only by a factor. And instead of adding a KL divergence term, we simply swap the factor representation between the two data points and then try and reconstruct the alternate data point. So with Z and Y prime for the data point X prime, we try and construct X prime and then use that loss through the network. And so this enforces reconstruction based off of the factor.
So we tried these losses on two data sets. The first one is rotated MNIST, where we interpolated between one dimension. And as you can see here, the regular VAE fails to fully disentangle, while similarity loss and cycle loss are more able to handle rotations during the interpolations. And we also trained a linear classifier on top of the latents. And as you can see, it performs much better with similarity loss and cycle loss than regular VAE. We also tried this on the chairs data set, and similar to what we found with MNIST, when you interpolate, here we interpolated with 3 latent factors. The similarity loss and cycle loss are able to rotate chairs, whereas regular VAE is not able to handle this task.
So we want to generalize the similarity loss to the celeb A data set. And so instead of the augmentation to create that X prime, we will just pair X1 and X2, which will be 2 images from the data set. And the additional constraint that we add is that the first 40 dimensions of the latent variable should correspond exactly to the 40 attributes of the celeb A images. And the idea is that by creating this correspondence, we can create easy interpolations within the latent space and also create explicit samples by setting certain latents to 1. And so the loss is now, if we have the common attributes between X1 and X2, which we call C, we will add a similarity loss, which is KL of X1 of C and X2 of C. And so we have some preliminary results that show the interpolations over just the first 40 dimensions of the latents. And the idea behind this is that by interpolating only over the first 40 dimensions, which is also the attributes, we will we will change the image's attributes while retaining the original image's noise.
So now we move on to the second component of our project, which is dealing with biased factors. So for example, what if the training data that we use to train our generative model is biased? Here's an example of that. We have an MNIST data set where every single digit is colored according to a specific color. But the test data set has randomized colorization. This means that when you train a simple classifier on the training data set, your test accuracy will be very low as it learns to just associate the color with each digit. So the way we remedied this representation for a VAE is by adding a bias predictor. Now our factor Y represents a source of bias in the data set, and we want to disentangle this biased factor Y from the latent representation D, or Z. We do this by learning a bias predictor to essentially predict what the bias is based off of the latent representation Z. And so this leads to a GAN-like optimization where the bias predictor tries to correctly guess the biased factor Y from Z, and the encoder tries to maximize the entropy of the bias predictor's distribution. Thus, we have Z, which Z becomes incentivized to be bias-free, whereas Y learns a disentangled representation of the bias. So some results on colored MNIST, we can essentially see that using a regular VAE, the interpolations aren't able to capture color very well. Whereas with the factor bias VAE, color is interpreted much better, and we see a much higher test accuracy on the dataset versus the regular VAE. This essentially means that we're partially learning to disentangle the information about color from the information from the shape of the digit in our latent representation.